Welcome to today's session. In this video, we will tackle LeetCode problem number 105, titled Construct Binary Tree from Preorder and Inorder Traversal. This is a fascinating problem that challenges us to reconstruct a binary tree using two specific traversal sequences. We'll break down the problem, explore the logic, and implement the solution step by step. Let's dive in. In this problem, you are given two integer arrays, Preorder and Inorder, which represent the preorder and inorder traversals of a binary tree, respectively. Your task is to construct and return the binary tree from these two traversals. The input consists of the two arrays, Preorder and Inorder, and the output is the root node of the reconstructed binary tree. This problem is a classic example of using traversal orders to uniquely define and build a binary tree structure. For the first example, the input preorder array is 3, 9, 20, 15, 7, and the inorder array is 9, 3, 15, 20, 7. The output is a binary tree that looks like this. The root node is 3, with a left child of 9 and a right subtree rooted at 20. The right subtree of 20 further splits into left child 15 and right child 7. To construct this, we start by identifying the root from the first element of preorder, which is 3. In the inorder array, this root divides the array into the left subtree, 9, and the right subtree, 15, 20, 7. Using this division, we recursively build the left and right subtrees. For example, the left subtree is constructed from preorder equals 9 and inorder equals 9, while the right subtree is constructed from preorder equals 20, 15, 7, and inorder equals 15, 20, 7. In the second example, the input is preorder equals -1 and inorder equals -1. The output here is a binary tree with just a single node, -1. Since there is only one element in both arrays, this single value represents the root, and the tree does not have any left or right children. This highlights the simplest case where the tree consists of just one node. Finally, in the third example, the input preorder array is 1, 2, 3, and the inorder array is 1, 3, 2. The resulting binary tree has a root node of 1, with no left subtree and a right subtree rooted at 2. Node 2, in turn, has a left child of 3. The construction process begins by identifying the root, which is the first element of preorder, 1. In the inorder array, 1 splits the sequence into an empty left subtree and a right subtree, 3, 2. Recursively, the right subtree is built using preorder equals 2, 3, and inorder equals 3, 2. This recursive approach ensures that the tree is constructed correctly based on the traversal orders. The constraints for the problem guarantee that the arrays are valid and the tree will always be uniquely determined. To solve the problem of constructing a binary tree from preorder and inorder traversal sequences, we can consider several approaches. One straightforward method is the brute force approach, which builds on the recursive definition of a binary tree. The key idea here is that the first element in the preorder array is always the root of the tree. Using this, we locate the root in the inorder array, which allows us to divide the array into left and right subtrees. Then, we recursively repeat this process for each subtree. However, this method has significant trade-offs. For each recursive step, we need to search the inorder array for the root, which takes n time. Additionally, slicing the arrays for each subtree adds further overhead, especially in cases of skewed trees. As a result, the overall time complexity can reach n squared, making this approach simple but inefficient for large inputs. To address the inefficiencies of the brute force approach, we can use an optimized method that relies on a hash map for constant time lookups. The intuition here is to pre-process the inorder array into a hash map, where each value is mapped to its index. This eliminates the need for repeated searches in the inorder array, significantly improving efficiency. The process involves defining a helper function that works with pointers to specific ranges in both the preorder and inorder arrays. At each step, we identify the root from the preorder array, locate its position in the inorder array using the hash map, and then split the inorder range into left and right subtrees. The recursive construction of these subtrees is handled by adjusting the ranges accordingly. This approach is more efficient, with a time complexity of n, for both pre-processing the hash map and constructing the tree, as each node is processed only once. While slightly more complex to implement, this strategy is far better suited for handling large inputs. Given the trade-offs between the two methods, we chose the optimized approach using a hash map as our strategy. The inefficiency in the brute force method stems from repeatedly searching the inorder array, which is avoided by pre-processing it for constant time lookups. This simple adjustment minimizes redundant work and allows us to achieve linear time complexity. The combination of the preorder array's root first sequence and the inorder array's partitioning property is key to this efficiency. By leveraging the hash map, we can adjust ranges dynamically during recursive calls without needing to modify the input arrays. The trade-offs are clear. While the brute force approach is easier to implement, its O(n) squared complexity becomes impractical for large inputs. On the other hand, the optimized approach, with its O(n) complexity, balances efficiency and practicality, making it the most effective solution for reconstructing binary trees from preorder and inorder traversals. To solve LeetCode problem number 105, we need to reconstruct a binary tree using two traversal sequences, preorder and inorder. Preorder traversal follows the order of root, left, and right, while inorder traversal follows left, root, and right. Understanding the relationship between these traversals is key to solving this problem. In preorder, the first element is always the root of the tree. In the inorder sequence, all elements to the left of this root belong to the left subtree, and all elements to the right belong to the right subtree. To make our solution more efficient, we pre-process the inorder array into a hash map that maps each element to its index. This allows us to quickly find the position of the root in the inorder array. With this understanding, we can begin constructing the tree recursively by dividing the preorder and inorder arrays into smaller sections corresponding to the left and right subtrees. The recursive construction of the tree begins by using key parameters such as preorder_index, which tracks the current root in the preorder array, and inorder_start and inorder_end, which define the boundaries of the current subtree in the inorder array. The base case for the recursion is when inorder_start exceeds inorder_end, indicating that no subtree exists, so we return none. To create the root node, we take the value at preorder_index, set it as the root, and increment preorder_index to move to the next root. We then use the hash map to find the root's position in the inorder sequence, which allows us to divide the inorder array into left and right subtrees. The left subtree is constructed using the range from inorder_start to one position before the root's index, while the right subtree is constructed using the range from one position after the root's index to inorder_end. Once both subtrees are recursively constructed, they are attached to the root node, and the entire root is returned. Using both preorder and inorder traversals allows us to uniquely reconstruct a binary tree because the preorder sequence determines the order of root nodes, while the inorder sequence provides the relative positioning of nodes. To optimize the algorithm, we use a hash map for the inorder array, allowing constant time lookup for the root's position, as opposed to the linear time required by the index function in Python. This optimization significantly improves the efficiency of the algorithm. By dividing the inorder array into smaller segments for the left and right subtrees at each step, we follow the divide and conquer approach, breaking the problem into manageable subproblems. The overall time complexity of the algorithm is O(n), where n is the number of nodes in the tree. This is because constructing the hash map takes O(n), and the recursive construction processes each node exactly once. The algorithm relies on several key data structures. The preorder array is used to determine the root nodes in the correct order, while the inorder array is used to define the boundaries of the left and right subtrees. The hash map, which maps each value in the inorder array to its index, enables efficient O(1) lookups for the root's position. The binary tree nodes themselves are instances of a tree node class, which stores the value of the node and references to its left and right children. With these data structures in place, we can efficiently implement the recursive solution. The Python implementation starts by pre-processing the inorder array into a hash map. We also use a list to track the preorder_index, ensuring it remains mutable and accessible across recursive calls. This setup forms the foundation for the tree construction. The implementation defines a helper function, array_to_tree, which takes inorder_start and inorder_end as parameters to represent the current subtree boundaries. If the start index exceeds the end index, it means there's no subtree, so we return none. The root value for the current subtree is taken from the preorder array at preorder_index, which is then incremented to move to the next root. A new tree node is created with this root value. Using the hash map, we find the root's position in the inorder array and recursively construct the left and right subtrees. The left subtree is built using the range from inorder_start to 1 position before the root's index, and the right subtree is built using the range from 1 position after the root's index to inorder_end. Once both subtrees are constructed, they are attached to the root, and the root node is returned as the result of the function. When implementing this algorithm, it's important to consider edge cases. If both the preorder and inorder arrays are empty, we return none since there's no tree to construct. For a tree with a single node, where both arrays contain only one element, the result is a tree with just the root node. Additionally, if the input arrays are mismatched, such as having different lengths or not representing a valid tree, the behavior depends on whether we handle invalid input explicitly or assume the input adheres to the problem constraints. By accounting for these scenarios, we ensure that the solution is robust and handles both typical and edge cases effectively. To begin constructing the binary tree, we define a tree node class that represents each node in the tree. Each tree node has a value, as well as references to its left and right children, which are initially set to none. Next, within the solution class, we implement the buildTree method. This method takes two inputs, the preorder and inorder traversal lists. The first step in this method checks if either list is empty. If so, it returns none, as there is no tree to construct. The key insight here is that the first element of the preorder list always represents the root node of the tree. Using this, we extract the root value and create a new tree node instance with this value. Then, we locate the index of this root value within the inorder list. This index allows us to divide the inorder list into two parts. The left subtree corresponds to the elements before the root index, and the right subtree corresponds to the elements after it. Similarly, we split the preorder list into left and right subtrees based on the size of the left subtree derived from the inorder list. Finally, we recursively call buildTree to construct the left subtree, passing in the appropriate slices of the preorder and inorder lists. Once the left subtree is built, we proceed to construct the right subtree. This is done by making another recursive call to the buildTree method, this time passing the slices of the preorder and inorder lists corresponding to the right subtree. After both the left and right subtrees have been constructed, we attach them to their respective positions in the root node. At this point, the entire tree has been reconstructed, and we return the root node. This approach ensures that we correctly build the binary tree while maintaining the relationships specified by the preorder and inorder traversals. Here, we start by defining the structure of our binary tree node with the tree node class. It includes an integer value and pointers to the left and right child nodes, both initialized to null. After that, we define our solution class, where the main method buildTree accepts two integer arrays, preorder and inorder. These represent the preorder and inorder traversals of the binary tree. The method first checks if either of the input arrays is null or empty, and if so, returns null, indicating there's no tree to construct. To optimize lookup times, we create a hash map to store the indices of values from the inorder traversal. This allows us to quickly determine the position of any value in the inorder array, which is crucial for dividing the tree into left and right subtrees. Next, we invoke a helper method named buildTreeHelper to construct the tree recursively. This method takes several arguments, the preorder and inorder arrays, their respective start and end indices, and the map we created earlier for quick lookups. Inside the helper method, the first step is to handle the base case where the indices are invalid, meaning we've processed all elements in a subtree. In such scenarios, we return null, indicating there's no node to add. The root of the current subtree is determined by the first element in the preorder traversal segment. We create a tree node for this root value and then locate its position in the inorder traversal using our map. This helps us calculate the size of the left subtree, which is the number of elements before the root in the inorder array. With this information, we recursively build the left and right subtrees by updating the indices to reflect the respective segments of the preorder and inorder arrays. Finally, the helper method constructs the right subtree using the appropriate segments of the preorder and inorder arrays. Specifically, we adjust the indices to focus on the elements after the root in the inorder traversal and their corresponding positions in the preorder traversal. Once both the left and right subtrees are built, we return the root node, which now represents the complete binary tree for the current segment. By repeatedly applying this process, the entire binary tree is reconstructed from the given traversals, and the build tree method ultimately returns the root of the constructed tree. This approach ensures we leverage the preorder and inorder properties effectively for efficient and accurate reconstruction. Here, we are given two traversal orders, preorder and inorder. Using these, we aim to reconstruct the binary tree. The process begins by identifying the root. In the preorder traversal, the first element is always the root of the tree. So, we take the first value, 3, and set it as the root. Next, we locate 3 in the inorder traversal to determine the boundaries of the left and right subtrees. The elements to the left of 3 in the inorder traversal, which is 9, belong to the left subtree, while the elements to the right, 15, 20, 7, belong to the right subtree. Similarly, we partition the preorder traversal to match these subtrees, giving us 9 for the left and 20, 15, 7 for the right. With these partitions in place, we now recursively build the left and right subtrees starting with the left subtree. To build the left subtree, we call the function with preorder equals 9 and inorder equals 9. Here, the first value in the preorder traversal is 9, which becomes the root of this subtree. Since 9 does not have any elements on either side in the inorder traversal, both its left and right children are none. This completes the left subtree, and we attach it to the root node, 3. Next, we move on to building the right subtree using preorder equals 20, 15, 7, and inorder equals 15, 20, 7. The first value in the preorder traversal, 20, becomes the root of this subtree. We locate 20 in the inorder traversal and split it into 15 for the left subtree and 7 for the right subtree. Similarly, the preorder traversal is split into 15 for the left and 7 for the right. Now, we recursively build the left and right children of the node 20. For the left child of 20, we use preorder equals 15 and inorder equals 15. The root of this subtree is 15, and since there are no elements on either side in the inorder traversal, both its children are none. For the right child of 20, we use preorder equals 7 and inorder equals 7. The root of this subtree is 7, and similarly, it has no children. Now, the right subtree of the root node 3 is complete, with 20 as its root and 15 and 7 as its left and right children, respectively. Combining the left and right subtrees, we have the entire binary tree reconstructed, which looks like this. The root is 3, with 9 as its left child and 20 as its right child. Under 20, we have 15 and 7 as its left and right children, respectively. Now consider a simpler example where the tree consists of just a single node. The preorder and inorder traversals are both 1. As before, the first value in the preorder traversal, 1, becomes the root. Since 1 is the only element, there are no left or right subtrees. This means both the left and right children of the root are none. The final tree here is just a single node with the value 1. Next, we have an example of a right skew tree, where all nodes only have right children. The preorder and inorder traversals are 1, 2, 3. The first value in the preorder traversal, 1, becomes the root. Since there are no elements to the left of 1 in the inorder traversal, there is no left subtree, and the right subtree contains 2, 3. The next value in the preorder traversal, 2, becomes the root of the right subtree. Again, there are no elements to the left of 2 in the inorder traversal, so there is no left child, and the right subtree contains 3. Finally, 3 becomes the root of this subtree, and since it has no elements on either side, it has no children. The resulting tree has 1 as the root, 2 as its right child, and 3 as the right child of 2. To analyze the time complexity of this solution, we start by looking at the operation to find the root index in the inorder array. This is done using the inorder.index root_val method, which involves a linear search through the array. In the worst case, this takes n time, where n is the number of elements in the inorder list. Next, we consider the slicing operations used to split the preorder and inorder arrays. For example, inorder, root_index, and preorder, 1:1 plus len, left_inorder, involve creating subarrays, and each slicing operation takes k time, where k is the length of the resulting slice. Across all recursive calls, the slicing contributes n time per level of recursion, given that the total elements across slices remain proportional to n. Now, let's consider the recursive calls. For each node, the function makes two recursive calls, one for the left subtree and one for the right subtree. Since the binary tree has n nodes, the recursion depth is proportional to the height of the tree. In the worst-case scenario, such as a skewed tree, the height of the tree becomes O(n). This means the O(n) index search operation is repeated at each level, leading to an overall time complexity of O(n squared). On the other hand, for a balanced binary tree, the height of the tree is O log n. Here, the recursive splitting happens in logarithmic levels, with each level contributing O(n). This results in a best-case time complexity of O(n log n). Thus, the overall time complexity depends heavily on the structure of the tree. Turning to space complexity, we need to account for two main factors: the recursion stack and the space used to store the sliced arrays. For the recursion stack, in the worst case of a skewed tree, the recursion goes as deep as O(n), leading to O(n) space usage. In the best case of a balanced tree, the recursion depth is O log n. For the slicing operations, at each recursive call, new subarrays are created for both preorder and inorder. Since the total elements across all slices are proportional to n, the space used for slicing is O(n). Combining these, the overall space complexity in the worst case is O(n) for the recursion stack plus O(n) for slicing, resulting in O(n). In the best case, it's O log n for the recursion stack plus O(n) for slicing, which still simplifies to O(n). Comparing approaches, a naive solution might try all possible combinations of node orders to construct the tree. This would result in an exponential time complexity of O(n), which is computationally infeasible. The current approach, while much better, still has room for optimization. By pre-processing the inorder array into a hash map that maps values to their indices, we can reduce the time complexity of finding the root index from O(n) to O(1). This optimization brings the overall time complexity down to O(n), since the slicing and recursive calls are now handled more efficiently. The space complexity remains O(n), due to the additional space required for the hash map and recursion stack. To summarize, the current approach has a time complexity of O(n squared, in the worst case and O(n log n in the best case, with a space complexity of O(n). The optimized approach, using a hash map, achieves both time and space complexity of O(n), making it the more efficient solution for this problem. When solving this problem, there are a few common mistakes to watch out for. First, not identifying the correct root node can cause issues. Remember, the root node is always the first element in the preorder traversal. If you fail to use this as the foundation of your recursion, the tree structure will be incorrect. To avoid this, always start with the first element of the current preorder subarray as your root. Next, incorrect subarray slicing is another frequent issue. This happens when the boundaries for the left and right subtrees are miscalculated while dividing the preorder and inorder arrays. To fix this, use the index of the root in the inorder array to precisely determine the left and right subtree divisions. Finally, inefficient lookups in the inorder array can drastically slow down your code. If you rely on repeated calls to list.index to find the root's position, the time complexity balloons to O(n squared). Instead, pre-compute a hash map of inorder values to their indices, allowing O(1) lookups and significantly speeding up the process. Another mistake to avoid is ignoring the base case in your recursion. If you forget to define a clear stopping condition, such as when the preorder or inorder arrays are empty, your code could end up in infinite recursion or throw out-of-bounds errors. The solution is simple: explicitly return none when the subarrays are empty. Additionally, misunderstanding the problem constraints can lead to incorrect assumptions. For example, assuming duplicate values are allowed when the problem specifies unique values can cause errors in your tree structure. Always verify the constraints carefully. Knowing that values are unique simplifies your solution and ensures correctness. These tips are crucial for building a robust and efficient implementation. Now, let's discuss some insights that can help you during interviews. This problem is a textbook example of divide and conquer applied to tree traversal. Recognizing how preorder provides the root first sequence and how inorder gives the left root right sequence is key to solving this efficiently. Additionally, utilizing a hash map for efficient lookups in the inorder traversal is an optimization worth highlighting. It demonstrates your ability to reduce time complexity and optimize performance. Be prepared to discuss edge cases, such as empty trees, single-node trees, or highly unbalanced trees, as these often come up in interviews. While recursion is the most intuitive approach for this problem, you should also be ready to discuss iterative solutions. Iterative methods often involve managing a stack manually, which can be challenging but is worth understanding. Lastly, related problems like constructing trees from other traversal orders or serialization and deserialization of binary trees are excellent ways to deepen your understanding and demonstrate your versatility. Finally, let's explore some alternative approaches to solving this problem. The recursive approach is the most straightforward and intuitive. However, it comes with the risk of stack overflow for deeply skewed trees, as the recursion depth can become too large. On the other hand, the iterative approach avoids these recursion depth issues by using a manual stack. While this can be more memory efficient, it introduces the challenge of managing the stack correctly, which can lead to errors. There's also a dynamic programming-like approach, though it's rarely applied to this problem. It may be useful for specific variations that require memoization, but it's not commonly needed here. Each of these approaches comes with trade-offs, so understanding their strengths and weaknesses ensures you can adapt to different scenarios effectively. Great work! To summarize, we successfully solved the problem by reconstructing a binary tree using preorder and inorder traversal sequences. Key takeaways include the importance of hash maps for efficiency and understanding traversal patterns for tree construction. Thank you for watching, and don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!